Hello everyone, my name is Andre Morgenstern. This is my final project for Controls of Automated Systems. My project is based on vehicle underlights for low speed use. Just a bit of background on underglow lights is that they're virtually found in every car culture in the world, even being famous in movies such as Fast and Furious Tokyo Drift. In Massachusetts, these lights are not legal, so this is technically a theoretical design for recreational purposes on show cars and for use on private property and private tracks and such. But the goals and functionality for this project are to have underglow lights on the vehicle with a master on and off switch, so it could be technically driven legally on the street. This master on and off switch, when turned on, the brightness on the LEDs at 0 miles an hour, meaning stationary, will be 100%, and at 25 miles an hour, these lights will essentially be at 0% brightness, so technically off. And the goal is to have a slowly decaying slope which allows these lights to be dimmable. For initial design, we have a drawing here, a rough sketch of a cross section of a car. We see the wheel well in which an infrared sensor is at an angle pointed at the rim. The rim has a reflective sticker on the inside from which the infrared sensor picks up on and is able to therefore determine the rotations per minute. How the system works, essentially the LEDs use 1.8 volts to 3.3 volts, meaning the operating range for these LEDs is 1.5 volts or essentially 1500 millivolts. The RPMs of the wheels captured by the infrared sensor is converted to miles an hour, and this equation distributes those 1500 millivolts of range by those 25 miles per hour, essentially leading to 60 millivolts per 1 mile per hour. Using the values just determined, we were able to figure out that at 25 miles an hour, the wheels turn at 7.011 rotations per second, and at 0 miles an hour, the wheels turn at 0. Using that, we can form an Excel graph from which an equation can be formed, where the x-axis has wheels rotations per second and the y-axis has millivolts input into the LED. So to create this model in Simulink, we need to understand exactly what's going on. So initially I have a ramp block which simulates the acceleration from 0 to 25 miles an hour in about 10 seconds, and this gets multiplied in the gain block by the circumference of the wheel initially, and then gets multiplied by the 3600 seconds per hour over 5280 feet per mile. This value gets subtracted from the 3300 millivolts that the LED uses at full power, meaning that as the speed increases, the millivolts into the LED decreases. On the bottom, I did a second simulation with 1500 millivolts, which is the range that the LEDs can use. So here we can see the graphs that the scope on the Simulink model was able to create. The top yellow line shows the millivolt values actually going into the system, and the bottom blue line shows just the range of the LED's functionality. So some concerns I've had about the system are that I did not take into consideration fast deceleration or acceleration, meaning if you were to slam your brakes, I think there would be an issue with the system. I say this because it was not considered taking certain readings over a certain time period, which would give an average, which would more accurately represent what is going on. But a average too long could also cause an delay in the system. That's it for my presentation. I appreciate it. Thank you, Professor, and have a nice summer.